So today I would like to present my, let's say, field of work, which is the statistical mechanics of neural networks. And I understand that you are a very diverse cohort of students and researchers. So I would like to give you, let's say, a broad overview. First, what statistical mechanics is, which is the first part of my title, with a bit of history and a simple application of statistical mechanics, an historical application that has been very successful to model real systems. And then I would like to pass to the application of statistical mechanics to supervised learning, which is, let's say, my research field. So yeah, I will sketch a simple case that we can study from the beginning to the end, essentially a simple neural network that we can study in this way. And then I will just spend 2 slides to present what I'm doing now at ICTP to motivate, let's say, the talk with a timely research topic. So let me start with a bit of history of statistical mechanics. What is statistical mechanics? So historically, it was devised to derive the laws of thermodynamics, knowing the mechanical laws of microscopical entities. You know that reality materials are done by atoms and molecules that are behaving simple elementary laws of electromagnetism or mechanics. But at the end, if you want to describe a macroscopic system, like the gas in a room, you just need thermodynamic quantities like the volume, temperature, and pressure to describe it efficiently. And so statistical mechanics was devised to understand what's the link between the microscopic degrees of freedom that compose matter and the macroscopic behavior of systems. But then it turns out that you can apply statistical mechanics to describe a lot of systems that are not, let's say, in the traditional domain of physics. Systems, for example, you can describe macroeconomies with statistical mechanics as systems with a lot of productive sectors that exchange goods and capitals. You can describe finance in this way as a system where agents are exchanging stocks. You can describe biological systems in this way. For example, genes are made of a large number of DNA bases, and this large number of bases are interacting in such a way that the genetic signal is expressed in individuals, and so on and so forth. So statistical mechanics, I will argue during this talk, is a good framework to describe systems even outside the traditional domain of physics, because it's essentially high-dimensional statistics applied to the system that you want to study. And in particular, statistical mechanics is successful in describing sudden qualitative changes in macroscopic systems that are usually called in our jargon phase transitions. Phase transitions are changes in macroscopical behavior of system, and you all know the liquid gas phase transition, the one you have in water when you boil it, and so on and so forth. You have other cases in various systems that you can study in these ways. One case that is not in the physics domain, but is in the neuroscience domain, for example, is when you are able to recollect memories in a neural network, or instead where you cannot, and this is also phase transition, and so on. So during this talk, I would like to convey the idea of what is a phase transition and how you can describe it with statistical mechanics. So history, these are the fathers of statistical mechanics, according to myself. Of course, you can go back in the past as far as you want. You can arrive to the ancient Greek philosopher Democritus, who was saying that matter maybe is made of atoms. I decided to stop to Avogadro, who is the father of modern chemistry, in a sense, who actually found evidence that indeed matter is made of atoms. And then these 3 gentlemen on the right are the people who actually managed to find the connection between microscopic degrees of freedom, elementary particles, atoms, molecules, with the thermodynamics observables. Maxwell, Gibbs, and in particular Boltzmann, who managed to find the link between statistical mechanics, the mechanics of microscopic degrees of freedom, with the second law of thermodynamics. So this is the program, the historical program of statistical mechanics, the way it was, the reason it was devised, which is to explain, for example, how a gas behaves. You have a set of molecules that are interacting among each other and among the walls of a container, of a box. And these molecules are very large in number. You have like 10 to the 23 molecules in a small space like this room. And each molecule, you can describe it with the position of the molecule and with the velocity of the molecule. So because these are vectors, you have 6n coupled equations that are describing the system. Equations because you basically assume that these molecules are interacting through the law of mechanics that Newton derived in the 17th century, in the 18th century. And these laws are deterministic. It means that if you have the initial condition for all the molecules for velocity and position, then you can follow the dynamics of this molecule through these equations, and you know whatever state of the system after a certain time. But then you realize that you don't need all this information to describe the system at the macroscopic level, so at the level that you're interested in this case, because you just need a few variables, which are just volume, pressure, and temperature of this ensemble of molecules. So what is the link between the mechanical description and the thermodynamics description, which is the one that you are interested to when you have so many degrees of freedom and you want to just to find this rough, let's say, description of the system. And the link was understood by Maxwell and Boltzmann is essentially the fact that you can take the position and velocity of each molecule as random variables. Because there are many, they are distributed in a very broad way, so you can take them as random. And then the thermodynamic observables, like temperature and pressure, are just the statistical averages over these degrees of freedom, these elementary degrees of freedom. For example, you take the velocity of each molecule, you square it, you find the average of it over all the molecules that you have in the system, and you find the temperature, and so on for the pressure. Okay? So this was the historical program of statistical mechanics, the first success of it. Of course, in this slide, I'm hiding a lot of subtleties that are at the foundations of statistical mechanics. I'm not telling you how a system has to be in order to be described in this way. There are many hypotheses that a system has to comply with for it being describable in this way. One of these hypotheses is the ergodic hypothesis, and to understand if real systems are actually complying with the hypothesis you need to derive this mathematical formalism is still an open problem in statistical mechanics and pertains the foundations of statistical mechanics, which is an active research line. And for example, just to give you an idea of what are these kind of fundamentals problems that you have the fact that mechanics, the law of mechanics are reversible, which means that if you invert the arrow of time, the dynamical processes that mechanics describes look all the time, all the same. So here you cannot tell if I'm playing this video in forward or in reverse, because the pendulum will look the same in both cases. But then the thermodynamics. Here you see the launch of the space shuttle, and you see that there are gases that are the ones that are launching the rocket that are going back into the tank. And this is not something that it's happening in real life. So you can see very easily that this video is played backwards in reverse. So where this irreversibility comes from when you pass from a mechanical description to a thermodynamic description is indeed one of the fundamental open problems in statistical mechanics and an open research direction. I won't touch these problems because you need seminars and lectures just to introduce statistical mechanics. I will just describe one case that where statistical mechanics can describe the phenomena in a good way, which is the phenomenon of phase transition. Phase transition, you're all aware of the ones of water. Water passes from being a solid, ice, at minus something degree. Then it passes to be liquid at 0 degree, and then it becomes gas at 100 degrees Celsius. And each time there is a change in the arrangement of the elementary degrees of freedom that are built in this system. And this sudden change, that is a macroscopic change, is what is deemed as phase transition in statistical physics. And with this kind of system, you can draw a plot, which is called phase diagram, which is telling you for each value of the control parameter of the system what phase the system is in. For example, this is a phase diagram in pressure and temperature, and each point of this phase diagram is telling you where water is once you fix temperature and pressure. So, for example, at 0, maybe you see my pointer, hope so. If you fix the temperature at 0 Celsius, and you have a pressure of 10 Pascal, you are the water is in the gas phase. If you start increasing pressure, at a certain point you meet a solid line, which is a phase transition, and you pass from being gas to being liquid, and then to be solid, and so on. So this is how you read this kind of plots. And every time you meet a continuous line, there is a phase transition. Okay? I hope so. Let's keep this as interactive as possible. I know it's an online meeting, but if you have questions, write in the chat or raise your hands. So the problem of water is that there is a lot of chemistry in water. The molecules of water have magnetic moments and other electromagnetic interaction between them. So it's very hard to study this phase diagram. So let me go to a model that I can, let's say, study from the beginning to the end in this talk. And this model was taught to model magnetic systems. Magnetic systems are systems that are able to attract iron. And we would like to understand how and what happens when I hit a magnet. Okay, so do you know maybe what happens if I hit a magnet? Let's do an experiment. And this experiment is an experiment where I put a magnet in contact with an iron bar, which is, so you can see the little magnet that is in contact with an iron bar. And of course, is attracted to it because it's a magnet, so it's the property of it. But then the experimentalist is heating the magnet with fire. And at a certain point, the magnet will reach a temperature such that, let's see, it's not able to attract anymore the iron bar. So the magnet falls down. Okay, and this temperature is found in this way, and it's called the Curie temperature. It's a critical temperature where the magnet passes from being magnetized, so being able to attract iron, to be non-magnetized. So this is a phase transition. We would like to explain this phase transition. And to do so, we will use a simple model. Okay. We will use a simple model to explain this phenomenology. And the simplest model you can think of is just a lattice, and which let's say model the crystalline structure of the magnet. And at each node of this magnet, of this lattice, I put a little arrow that is modeling the microscopically degrees of freedom that are small magnetic moments of the molecules that are composing the magnet. And you see that you can imagine that at high temperature, all these arrows will be pointing in random directions. And so you will have no net magnetization of the system. And so the system will not be able to attract iron because there is no macroscopic magnetization, because if you sum all these arrows, you find on average 0. And then you will have instead a low temperature phase where all these arrows will tend to align in the same direction, and the sum of them will produce instead a macroscopic magnetization, and so it will be able to attract iron. So we would like to model magnetic system in this way. And so in this slide, I will present the statistical mechanics problem to solve these systems. So you have elementary degrees of freedoms that are these pins. These little arrows that I put on the lattice. And in the simplest case, they can be or +1 or -1, okay, or up or down. Then you have configurations, which are just collections of these pins, n, which is the number of sides of my lattice. And so configurations are just point in a high-dimensional space, which is the vertex of this hypercube of ±1. And then I have a function over this configuration. This function is telling me how the elementary degrees of freedom are interacting. Okay, so it's basically telling me what is the cost that I pay. So let's look at the first term, which is this sigma I, sigma j. This is the cost that I'm paying every time I'm misaligning the spins, because when the spins have different sign, one is plus and the other is minus, this combination is negative. With a minus sign, I get a plus, so I get a plus j every time I misalign two spins. When I align them instead, I get minus j, and so I'm getting a lower, let's say, energy cost to align them. And then I have also a term that is telling me that if the spins are aligned to, so have the same sign of a certain number h, then I pay no cost, or I pay some cost if I misalign the spin to h. Okay. This is called Hamiltonian, and it's telling me how the spins are interacting. This sum I in j is restricted to neighbors in this lattice. So let's say that the center spin interacts with the neighbors that are the ones connected with the gray pattern, but not with the ones that are not. This is the Hamiltonian. And then I go to Gibbs, Boltzmann, Maxwell, that are telling me what is the probability distribution of a configuration of this system. Knowing the Hamiltonian, the probability distribution is given by one parameter exponential family, which is just the exponential of this parameter beta times the Hamiltonian over a normalization factor. For the moment, you think of this just as a family of probability distribution that are parameterized by this beta. We will see in a second what beta is. And just notice that this is a good probability distribution because it is positive, because it's an exponential of a number. And it's normalized because this factor at the denominator is just normalizing this probability distribution. It's just the sum of all these exponentials over all the configurations. Okay, and from this probability distribution, you can derive macroscopic quantities, which are just the average of microscopic quantities over this probability distribution. And the way you do so, you, for example, define a free energy, which is the logarithm of this partition function. And then you can, for exercise, you can observe that if you derive, for example, the free energy with respect of the field H that is appearing in this Hamiltonian, you get the expected value for the spin, which is the macroscopic magnetization, which is the observables that you would like to access to describe this magnetic system. Okay, I still have to tell you what is beta. Let's see if we manage to interpret it. So first of all, let's take beta equal to infinity. So when beta is large, you have that this probability distribution concentrates over the configurations of the spins that are minimizing this Hamiltonian. This you can see because the probability distribution cannot be zero everywhere, because otherwise it wouldn't be normalized. It wouldn't be normalized well. So it has to concentrate somewhere. The partition function, which is at the denominator, is a sum of exponential, and the lowest, let's say the biggest of this exponential, because beta is going to infinity, is the one where h is minimum. So this partition function is basically this quantity plus the rest, and so the probability distribution will concentrate on this value. What is the configuration that is minimizing the Hamiltonian? Well, it's the one where all the spins are aligned, because in this way you minimize this first term, and then they are all aligned with the external magnetic field. Okay, so when beta is going to infinity, this probability distribution over configurations is concentrating over this particular configuration, and it will be zero for all the others. What happens instead when beta is zero? Well, for beta is zero is easier. The exponential of zero is 1. And z to the n, the partition function, is just the sum over all the possible configuration of 1. How many configurations I have? 2 to the n, because each spin can be or plus or minus 1. I have n of them. So the probability distribution of a configuration is just 1 over 2 to the n, the number of configurations. And this means that basically all the spins are just coins that can be head or tail with equal probability without interacting with each other. Independent coins, let's say. which means that all the spins will be aligned randomly, and if you take the average over them, you find 0. So we found that this probability distribution for beta infinity is giving you that the spins are all aligned, and for beta 0 is giving you that the spins are randomly aligned, and so there is no magnetization. Which means that this parameter is the inverse temperature, essentially. Is a parameter that is telling you that when the temperature is low, you have that the spins are all aligned, and when the temperature is high, which is beta equals 0, you have the spins random in random positions. So this is the statistical mechanics program. I let you notice that, let's say, you read this slide, you believe that the problem is solved because I gave you everything. I gave you the Hamiltonian. I gave you what's the probability distribution of a single configuration, and so you can solve the problem. But the hard part here would be to evaluate the partition function, because the partition function is a sum over an exponential number of values that are the configurations, and this sum is hard to do in practice. So usually the bottleneck of a statistical mechanical approach is to evaluate this partition function. Once you have it, you can derive all the thermodynamic observables doing, let's say, derivative of functions of this partition function. And then you can do, let's say, simulations of the system I just presented. And for example, you can measure in simulations what is the average magnetization of the spins. So you run, you sample at equilibrium the probability distribution that I show you, the Gibbs-Boltzmann, and you measure, let's say, for each configuration, what is the magnetization. And you see this kind of profile. You see that at high temperature, the magnetization is essentially 0, and at low temperature is going to 1. And this behavior is smooth as long as you have a finite number of spins, but it's becoming more and more steep when the spins are increasing, when the number of degrees of freedom are increasing. And the behavior will be non-analytical, so this would be a sharp transition when n is going to infinity. And this is what is a phase transition. So it's telling you that there is a phase of the system when, in this case, where the temperature is high, when magnetization is 0, and another phase when magnetization is 1. So magnetization is usually called the order parameters because its value is telling you which kind of order the system has, if magnetized or not. Okay. This concludes, if you want, the part of magnetic system, which was a bit boring. But then people soon realized that you can use this kind of approach to study many more problems that are outside the domain of physics. You can study economy, ecology, biology, medicine, social sciences problem in this way. And if you just want to have an idea of the richness of this framework, you can just check the quantitative life science research directions, which is the section of ICTP I'm affiliated to. And you will see these rich interests of our community to exploit statistical mechanics approaches to study interdisciplinary application, which is, I think, is the most interesting part, at least for me. And let's say, just to give you some ideas, this essentially a flock of ships that are at a certain time scale and very far in the sky, they look like a liquid. So you can describe them with statistical mechanics. Or this is even more dramatic. This is the crowd at an Oasis concert. And at a certain point, you see a collective behavior that is a wave along this crowd of people moving. And so this looks also like a statistical mechanics problem where the collective behavior is actually the thing that you would like to control, because it's very hard to control crowds and so on and so forth. So let me go to a specific application of statistical mechanics, which is the study of supervised learning. And in order to do so, I would like also to introduce what supervised learning is. And so let me do with this slide. So supervised learning is a framework where you have a training set, which is, for example, a set of images coming with a label. So each each image comes with a label that is telling you what's inside the image. It's an annotated training set. And the thing you would like to do is to train an algorithm using this set of examples that is able, at the end of the training, to label a picture that the algorithm never saw before. Okay, so using the examples, you train, and then at the end you show the algorithm a new picture, and the algorithm should be able to label the new picture with the correct label. So this is the framework of supervised learning. And it's the framework that is successfully solved nowadays by neural networks. So we will study how you can use neural networks to solve these problems. Let me first explain what's a picture, because as long as I show you the picture, it's hard to do mathematics on it. So for me, a picture is just a collection of pixels. In this case, 32 times 32 pixels. Each of them can have a color, and let's say a nice way to codify colors is just using an RGB scheme. And so you have essentially 3 numbers for each pixel. And so you can represent an image as a vector in high dimension. Okay, where these dimensions are the number of pixels times the number of colors in each pixel. Okay, so for me, images are just vectors in a high dimensional space, let's say D. And then I want to train a neural network that is able to label these pictures. So the simplest case is called perceptor, and is basically taking the picture, which is a vector in high dimension, is projecting it with a set of weights, this vector W that you see in the slide. And then it's applying a nonlinearity, an F function that you can take it as a sine function, for example, to this inner product. And the result is the label. You can think of doing binary classification, which means that I will send the slides at the end of the talk, yes. I don't know if you have troubles in seeing them, otherwise I can also send them before if you want to follow. Let's see. You can imagine of doing binary classifications of these in this setting. For example, you want to distinguish cats from dogs. So in this case, +1 will be cats and -1 will be dogs. So you take an image of cats or dogs, you take an inner product of this image with your parameters, and then you take the sign. If the sign is plus, they say it means that the network say that it's cat. If it's minus, it says it's dog. So this is the idea. How do you pick the parameters? Yes, let me go to the equation, which is this one. How do you pick the parameters? Well, you have a training set, a set of examples. You define a loss function, which is a function of the parameters that is measuring how well you are doing on the training set, which means that you are comparing the true labels that are this y, iy, y of I, of the set of examples that you have, with the predictions of the network. The prediction of the networks, as I told you, is W times Xi, times with the nonlinearity applied. So if the loss is 0, it means that you are already fitting perfectly the set of examples that you have. If it's different than 0, you have to move the weights, because it means that they are not good enough. And the way you do this, you do gradient descent. Okay, you want to minimize this loss, which is actually measuring the mistakes you are doing in your training set. Okay, this is gradient descent, which is the standard algorithm to move the weights to minimize a function. Okay, and so you have also, let's say, geometrical interpretation of what the perceptron is doing is evaluating the scalar product between the set of weights and the inputs, and is putting a label according to if the inputs are coming on the left or on the right of this plane. So you see that a vector in high dimension is parameterizing a plane, and then if the points are coming on the right are red, and if the points are coming from to the left are blue. Okay, so a perceptron is essentially implementing linear classification in an high dimensional space. It's a simple model that can do this. You can ask how long ago was this machine proposed? Well, the perceptron itself as a model for artificial neurons was proposed in the 40s, in 1943, by McCulloch and Pitts, who were neuroscientists and wanted to model the brain in this way, as a simple neuron, let's say. But then the implementation of a perceptron as a machine able to do this is from Rosenblatt in 58. So at the time, computers were filling rooms. And here you see an experimentalist in the 60s that is training a perceptron showing pictures of man and female. And here is doing essentially gradient descent to fit the parameters of this perceptron, that in this case were resistors, to be able to classify men from women and so on. Okay, so this is not a new idea. It's an idea that comes from the 50s, and it's one of the first approach to artificial intelligence. It was forgotten for many years, and now we are back into studying neural networks because people realize that they work. Let me go to the statistical mechanics approach of this. You see that I presented a case where you have a training set, which is this set of input-outputs. Yeah, I cannot control the record of the lecture, but I think the organizer will be able to do this. So you have this set of input-outputs. You have a parametric function, which is this neural network that is mapping the input to the outputs. And you have a loss function that is measuring how good you are doing on a training set. And you see that you can write this as a statistical mechanics problem, as I did before for the Ising model, where the thing that I called Hamiltonian, that was measuring the cost, the energetic cost of misaligning spins, is now this loss function. It's telling you how good you are, what cost you pay every time you are mislabeling a point in the training set. And then, of course, your elementary degrees of freedom that before were the spins, now are just the parameters of the model. So you have a statistical mechanics ensemble in this way, and you can study the partition function. Many researchers started doing this from the 80s, let's say. Here I want just to present Elizabeth Gardner, who was one of the strongest researchers working on this at the time. And she published many seminal papers on this, on which we are still working on. And in particular, Elizabeth Gardner was interested in studying the problem of expressivity, which means to count, let's say, how many classifications a perceptron can do in general. Because a perceptron is a simple model, is linear. You can actually understand how many classifications you can implement with a perceptron. And the way she did this is to study the worst case possible for generalization, which is the case where the labels of the points are random. Okay, you have these images in high dimension, these points in high dimensions, and you just put a random label on it. Okay, so there is no real input-output map that is sending the input, the images to their label, but the labels are assigned randomly. And the reason to study this kind of problem is to consider, let's say, if the perceptron is still able to fit this training set, even if there is no rule to learn. You see that in terms of generalization, you will never be able to generalize on new examples because the labels are assigned randomly. So you will be, with probability 1/2, you will miss the new label. But still you can ask questions like, okay, can I still fit this training set even if the labels are random? And these questions are linked to the expressive power of a perceptron. It's telling you how many possible different classifications a perceptron can implement. And the way she studied this problem was to consider this partition function, which is an integral, which is like a sum over configurations over our weights, of a particular kind of loss function that is just the set of constraints given by your training set. Basically, here you are asking that W times X has the same sign of Y, that is the label assigned to the input X. And then she put also a positive constant kappa that is making these constraints more difficult to solve. So this theta function is an Heaviside step function that is 0 if the argument is negative and is 1 if the argument is positive. So this partition function is simply a volume that is counting the number of configurations of the weights that are solving this set of constraints. And studying this problem, Gardner managed to draw a phase diagram for this problem in the similar way that you can draw for water or for magnetic systems. And you see that in a particular limit where you have that the number of examples in your training set and the dimension of your program they are both going to infinity with the ratio finite to a certain constant alpha. This phase diagram is telling you that there is a phase where there is no W able to solve these constraints. And then there is another phase instead where alpha is small when there are many W's that are able to solve this constraint. Okay, and in between the two, you have a phase transition. Okay, so this is an approach where statistical mechanics proved to be useful to study neural networks. Okay, let me just tell you that alpha is just the number of constraints over the number of dimensions you have, number of degrees of freedom. So this is a natural parameter that you can tune in this kind of problem. And by tuning it, you pass from being able to fit a training set, even if the labels are random, to not be able to do it at all with a perceptron, which means that your set of points and labels are not linearly separable by a plane. There is no plane able to, let's say, implement the classification. Okay? This is one of the first cases where statistical mechanics was used at the end of the 80s to study neural networks. And then let me go to what we are doing now, let's say at ICTP. You see from this slide that we are not so far from perceptrons, regardless of our best efforts in the last years. But still we are making progresses. And now we are studying networks where there are two layers. So we are studying deeper networks. And two layers means that we have an input X that is multiplied by a matrix W. Then you have a nonlinearity sigma that is applied element-wise to this combination. And then you have a vector readout V that is just taking this number and projecting it into a scalar. So it has been asked, what is the main variable? Is it X or W? So X here is just a fixed realization of the training set. So the degrees of freedom are W here in this problem. X, let's say, is a random variable that is coming from the fact that you decide to take a certain distribution for the inputs and a certain distribution for the output. So if you want to do at the end average values, so if you want to evaluate average values for the thermodynamic observables, at the end you will need to average the thing you obtain over the distribution of X and Y. But at this level, the elemental degrees of freedom are the weights. And here you basically choose the weights in such a way that these constraints are satisfied, if you may. Okay, in this other setting, you choose the weight in order to minimize this loss function. And one way is, for example, to do gradient descent. Okay, maybe I'm not sure I answered. I hope so. Okay, so this is the application that you are studying right now at ICTP, which is a shallow network where we have one layer more, and this network is much more expressive than the perceptron. As I told you, the perceptron can at most implement linear classifications, while this machine can, in principle, implement more complicated rules because it has this nonlinearity sigma between the two layers. And there are, for example, universal approximation theorems that are telling you that given enough neurons in the hidden layer, you can approximate any function. So this is a universal approximator. So let's say the expressive power of this machine is much bigger than the one of the perceptron. And the thing we are doing now is to study how this network generalizes in a specific regime where the number of parameters of the network, which is, because the parameters are W and V here, is just the dimensionality of this matrix plus the dimensionality of this vector, which is KD plus K. So it's a regime where the number of parameters are scaling like the number of data. So it's a regime where indeed the network if the network wants to fit the training set the best it can, it has to move all its parameters because it has a comparable amount of information inside the training set. Okay, and we want to study generalization. To study generalization, we basically ask, okay, let's assume that the labels in the training set are generated with a neural network with the same architecture. And the task of this neural network here, the student, let's say, is to understand what are the weights, V and W, that the teacher has used to generate the labels. Okay, it's a teacher-student setting in the sense that there is a teacher network that is putting labels on top of points through this machine. And then there is a student network, same machine with different weights, of course, that wants to tune its weights in order to match the ones of the teacher. Is this machine able to do this or not in this regime? This is what we want to understand. Because if we want to understand, if we understand this, we can tell what is the mechanism by which this machine is able to generalize, to understand what the rule is. Okay. And this is what we found. We found a phase transition even in this setting. And in this phase transition, the thing that happens here, I'm plotting the generalization error, which is the error you are doing on a new point that the machine never saw during training. And in the behavior of this generalization error, you see that there is first a branch where the model, the generalization error is behaving smoothly and going down along this blue curve. And then you have a sudden drop in the generalization error where it goes down faster. Okay? And this behavior is linked to two phases in the system. There is first a phase where the system is not able to understand the target function, so the teacher, but it's only able to find an approximation of it, a polynomial approximation of the target function. And then in this sudden drop in this phase transition, the model is actually able to realize that the teacher has the network structure that we implemented, and so he's doing much better because he's able to fit actually the weights of the target function. And this is the reason why the generalization error is much smaller after specialization than before. So here is a case where we are able to study the phase diagram of this system. This phase diagram has two non-trivial phases separated by a phase transition. And these two phases correspond to different mechanisms by which generalization occurs. First, you only learn approximations of your target function, of the rule that is mapping input to output. And then instead you learn the rule by itself, aligning to the teacher network. So this is, let's say, this work has been done during the last year, and we are happy because we are able to fit. You see, basically the numerical points are going on the curves, so we can say we understood this case. Okay, so these are the take-home messages of my talk. Let's say I presented statistical mechanics as a framework to study systems in high dimension. Okay, it's a pretty robust framework that you can apply in many contexts. I presented the case of physics, which is magnetic systems, and I presented the case of neural networks. You can use statistical mechanics for many other interdisciplinary applications. And the focus of statistical mechanics is to study collective behaviors of degrees of freedom. You are not interested in what a single spin is doing, but the fact that all together interacting are generating a magnetic system, a magnetic field. Or you are not interested in studying what a single parameter in a neural network is doing, but you want to know how the neural network by itself generalizes, or what is the expressive power of neural network. And this is a collective observable of the system, a macroscopic property. And then in the case of machine learning, I show you that machine learning is an high-dimensional problem because whatever input you are thinking of, images in the case of classification I presented you, but also text if you want to study large language models like ChatGPT, all these input points are vectors in high dimension. And so machine learning has this characteristic of being high-dimensional statistics. And as I show you, statistical mechanics provides sharp predictions for the behavior of this network in certain asymptotic regimes that are the ones where statistical mechanics works better. And with this, I thank you for your attention.
Thank you, Mauro, for this nice lecture. And now we can open the session of questions. If someone has a question, he can raise his hand or her hand. Anyone has a question, please?
I also would like to thank you, Mario, for this interesting talk.
Yeah.
Yeah,
Thank you again
really, it really makes a very great connection between Ising model, statistical mechanics, and machine learning. And so seeing all these beautiful pictures, which you might at some point pick the right picture for a cat, for example, just by identifying the right vector and the right width, and then you will be able to get the right results. Yeah, it's very interesting. Thank you.
Okay, I'm happy you liked it.
Yeah, you want to add, Hannah?
I already asked him during the lecture.
Okay, the audience, the participant, do you have any questions for Mauro? The question in the chat, Mauro.
Okay, let me write it for all. So I have a question. If the universe inevitably moves towards maximum entropy according to the second law of thermodynamics, yet models such as convolutional neural networks and k-nearest neighbors extract ordered features from stochastic data distributions, does the reduction of informational entropy h of x sound okay, the Shannon, within the model's internal representation imply that intelligence locally minimizes entropy only to maximize global thermodynamic entropy at a faster rate? Okay, this is a tough question. I'm not sure I can answer it. Okay. So I think I can say, first of all, is that to train neural networks, you need energy. And once you spend energy, you can reduce entropy because this is not a closed system because you are putting energy in it. You can ask what happens to the entropy of the universe every time you train a large neural network or an inference model, and I guess that there will be a net rate of entropy production that will be positive. But I don't want to enter into this a very broad and fundamental question that I don't know how to answer, actually.
Okay. Someone else? Hannah?
Okay. I would like to ask a question. So first of all, it will be, for example, for the phase diagram. It will be data taken from experiments, and then you interpret it by the theory and machine learning, or the other way around. You start with some theory and do an experiment.
So how do you are asking how do we proceed?
Yes.
Okay. Let's say that depends very much on the problem at hand. Here I would say that we moved in parallel in the sense that we, let's say, tried the theory and experiments at the same time. Because let's say the hard part in this problem was to identify the right statistics to look at. Okay. In the case of the easing, I told you what is the right statistic because it's just the average value of the spins. This average value is the thing that is giving you the total magnetization, the macroscopic magnetic field that the model is able to exert. Here, it's not so trivial to understand what are the statistics that are the fundamental statistics that are important to describe this model. And to found them, we used the numerical simulations also in parallel with the theory to understand what they were.
Okay.
Because let's say finding the right statistics, the sufficient statistics of ensembles is the thing that allows you to evaluate the partition function, which is the hard part. You cannot do it exactly you cannot even do it computationally because you have to sum an exponential number of configurations. And so the way you do it in practice, you find the sufficient statistics that is describing your ensemble. And then in this way, you manage to do dimensional reductions. So instead of having a large dimensional integral to evaluate the partition function, you have just an integral over the values of these order parameters that you are studying. And in this way, you manage to evaluate the partition function using saddle point integration and this kind of approximation of integrals. So the hard part of this problem that I presented was to identify what were the sufficient statistics of the ensemble that were able to describe the two phases together. It was the hard part. And now that we understood them, we realized that these sufficient statistics are linked to the mechanism by which the model learns. In the first phase, indeed, the model is not learning the weights of the target function by itself, but it's learning only combinations of these weights, non-trivial combinations that are the ones that the models are learning. And then instead, after specialization, the model is able to align with the weights themselves of the target function. The target function has matching structure with respect to the network. And so you can actually measure how this matrix W is close to the matrix W of the teacher, and how this vector V is close to the vector V of the teacher. Let's say these comparisons are allowing you to find order parameters that are telling you how big is this overlap between teacher and student. And the description of these order parameters, the solution of them, allows for plotting the theory here. So coming back to your question, in this particular case, we were both following theory and experiments, I would say, in a parallel way, let's say. In other case, you have priors on what your order parameter should be. For example, you can think of which kind of symmetries you have in the problem, and the order parameters that are breaking these symmetries could be linked to a spontaneous breaking of a symmetry, which is what happens in magnetic systems, because in that case, you have a single direction where now the model is aligning, and so on and so forth.
Okay.
Thank you very much. It's clear now. Thank you.
Someone else, if you have any questions, please. There is someone who asked about the presentations. I will share it with you by email.
I will send you the slides to you, Kamel or Hala, and then you will share.
And I will share it with WhatsApp, the group I have provided.
Perfect.
At the end, we would like to thank you, Mauro, again for your effort and this nice presentation. Also, big thanks for Jean Barbier and his patience to be with us during this hour. And we hope also Mauro and Jan like to see you in the next lecture. For sure, it will be great, your attendance and your interaction too. And Hannah, you would like to say thanks again, yeah?
Yes, of course. I would like to thank Mauro and Jan for being with us today and for giving us this nice lecture. And we will be happy to see you in the next coming lectures for sure. And also I would like to thank all the people who joined this lecture and hope to see them also in the coming lectures. Thank you all.
Maybe like there is a question. There is another decision. Yes, we have another decision. It's in Frontier for Physics Without Frontier website. We will share it with you also. There is a question, Bashar Saleh. I don't know. It's up to Mauro if he want to answer that.
Can the Bayesian evidence be seen as the statistical partition function where inference seeks configuration that minimize free energy? And again, thanks for... Okay, yes, of course. So this framework is essentially a Bayesian framework. So the partition function is the normalization of the posterior of the weights given the data, which is the evidence. And you can think of taking this partition function and let's say taking this ensemble and sample this posterior, and in this way you will do statistical mechanics at temperature 1, because this is the usual setting for the temperature in a Bayesian framework. Or in the case I presented in the slide, which is the empirical risk minimization, you have the loss and you want to find the parameters that minimize it, will correspond to the cases where you send beta to infinity. You want these posteriors to focus only on the minimal values for the loss. So yes, you are completely right. There is a precise mapping to Bayesian learning.
Okay. Thank you, Mauro. Thank you, Jean Barbier. Again and again, thank you for this big efforts, and hope to see you in next seminars. And we are also looking forward your support continuously for us. Without your support, Jean Barbier, we will not be able to do this series. And thanks for introduce Mauro for us. It is really a nice topic. And that's it. And have a good evening. And in Italy, ciao, yeah?
Goodbye, everyone.
Everybody has a good evening. Goodbye. Ciao, ciao.
Bye, everyone. Thanks a lot again.
Thank you.
Ciao.